All right. So, from next week onwards, I'm going to change my office hours from Monday afternoon to Monday and Wednesday morning from 9 to 10. Okay. So I'll be out Monday afternoons. Today I'll be in there from 2:30-ish to 3:30 perhaps. And then from next week onwards, Monday afternoons, I won't be in the office. I'll make the change on the office hours page on the website. So everybody should have that information. Okay, this notebook. And let's go to chapter 2. So we rushed through this a bit last class on Friday. Let's go into a little bit of detail. So this shows the cross-sectional view of a typical NPN transistor, right? We looked at PN junction diode, P-type semiconductor brought in contact with an N-type semiconductor. Now we add another junction, and we can create a PNP or a NPN transistor. Everything that we discuss here would be primarily for NPN transistor, but everything that we discuss for the NPN transistor applies equally to a PNP transistor. Okay, the only difference would be that the voltage polarities and the current directions would be flipped because the electrons and holes would be interchanged. For instance, here I'm showing you the side view or the cross-sectional view of a NPN transistor. And because it's an NPN transistor, the majority carriers are electrons. When we talk or discuss a PNP transistor, the majority carriers would be holes. Okay, but the operation remains the same. So this is the side view. Let me draw out the top view and explain how these are actually built. Okay. So let's and this is what a typical silicon wafer would look like, substrate, right? This is looking at it from the top. And again, today forgot to bring wafers for show and tell. And you don't have to draw these out. This is just for explanation purposes. An entire silicon wafer. This is, let's say, typical academic wafer would be about 4 inch in diameter or 4 inches in diameter. Production wafers or facilities are typically 8 inches or 12 inches in diameter. So big circle, flat circle. The thickness is typically about 500 microns. So basically as wide as a 0.5 millimeter pencil, right? You have those mechanical pencils with those leads in there, which is 0.5. So a silicon wafer about 4 inches in diameter is about that thick, 500 microns. I should say that thin, really. And then we build, since we are talking about the micro scale, we actually build at it from the top. We do surface micro machining. So mostly just X and Y direction. We simply use the top few microns out of those 500 microns of thickness of a wafer. We are simply using the top surface, meaning the top 1 or 2 microns. Okay, we are not even going into the Z direction. And the way it works is, let's say we have one single chip and one single transistor inside a chip. So this would be one single chip. And this chip would have an entire circuit, and the entire circuit would have tiny devices spread everywhere, right? And one tiny device is this one transistor. So there would be hundreds of millions of these transistors. And I'm just showing you one of these devices, okay? Nowadays, VLSI scaling means we have approaching like billions of transistors in one single chip. So the amount of quantity of transistors we are able to fit on one small tiny space is just mind-boggling to me at least. So this would be the top view. All of this is the top view. So if we are talking about an NPN transistor, we would say we have a N-type silicon wafer. Looking at it from the top, we create a small opening in our N-type wafer. Okay, and then we implant or we introduce P-type material in there. So looking at it from the top, you have an N-type silicon wafer. We create a small opening and we introduce P-type material in there, or P-type impurity dopants. Thus, we now have a PN junction diode. Make sense? Then inside this P-type material, we create another small opening. And now we introduce N-type impurity material in there to create a enclosed N-type junction or NP junction. So this is N-type. This is P-type in green. P. Does that make sense? Right. This fabrication, which I just talked about in a brief few minutes, is an entire industry by itself. Okay, which is what you hear about the chip wars that have been going on for the last few years. So it all started in the 1960s here in Silicon Valley. Intel was the world leader for a long time, and then they shifted manufacturing. They didn't shift it. It's a very niche industry to break into. Each piece of equipment that we use for this processing costs millions of dollars. Even in an academic clean room, one of the cheapest equipment that we can use is probably about $250,000 or $500,000. Okay, even in an academic clean room. So we actually do have a semiconductor fabrication facility here on campus. How many of you were aware of that? 1, 2, 3, 4, a few people. The reason I'm bringing it up is because it's an avenue for engineers to go work in. So that's my specialization. My specialization as a graduate student was in microfabrication, semiconductor fabrication, and MEMS. MEMS stands for micro electromechanical systems. It's where we build mechanical structures on a microchip. And inside a clean room, we have people from all backgrounds: engineering, science, physics, chemistry, chemical engineers, mechanical engineers, biomedical engineers, electrical engineers. Everybody comes together and works inside this clean room. So that is an avenue. If you're searching for jobs after your graduation, that's an avenue or a field that you could look into. I had lots of fellow students working with me. One of my best friends and one of my roommates was a chemical engineer. They went to work for Intel. Okay, so the reason I'm just bringing this up is because it's a career that not many people are aware of, but it hires a lot of people from all backgrounds. Okay, it hires a lot of people from all backgrounds. And increasingly, as you might have, if you have kept up with current news, you know that there's a big push to increase semiconductor manufacturing back in the US. A lot of these plants are being built right now. It takes about 3 to 4 years for them to be fully operational and come online. So right now they are actually looking for engineers to work in those plants. Okay. In the academic clean room that we have here at Cal Poly, we offer a class that's offered only in the winter, once a year, where students actually go inside the clean room and build diodes, resistors, electronic devices, and learn about semiconductor processing. And that's open to students of all majors. Okay, it's only offered once a year. So if you have an opportunity, you might want to look into that. It's BMed 434, BMed 435, theory and lecture. It's also cross-listed with EE. There's a lot of students from ME also who take this class. Anyway, so coming back to our structure, does the side view and the top view, does the explanation make sense? Right? Okay, so then let's look at what makes it special. So we said that there are two PN junctions in a transistor, right? And normally you would say if it's a PN junction, it should work like a diode. But that depends on the DC voltages that we apply. So because of the structure, and let's go back to that slide again, and I'll recap. Because of the structure of a BJT, we can see that the emitter is the smallest in size in the X and Y direction, right? This is the X and Y direction. So the emitter is the smallest in size, is basically enclosed inside the base, and the base is then enclosed inside the collector. So physically, the collector is the biggest in size, emitter is the smallest. And then the base is the thinnest. And now we're talking about the Z direction. Okay, so this is the Z direction going into the wafer from the top. And this would be the X and Y direction. So base is by far the thinnest. Collector is by far the biggest. Emitter is the smallest in the X and Y direction. Okay. However, the emitter is the most heavily doped out of all three, meaning it has an excess of free charge carriers. It's an NPN transistor. The emitter is made out of N-type material, meaning it has a lot of free electrons. In a PNP, the emitter is made out of P-type material, meaning it has an excess of holes. So whether it's NPN or PNP, the emitter has the most amount of free charge carriers. And then if we forward bias the base and emitter junction, that means that the electrons or the carriers from the emitter are free to cross over into the base. Okay, they're free to cross over into the base. But the operation of the base and the collector junction is not like a true PN junction because we reverse bias it. So we apply positive to the base, negative to the emitter. We forward bias the base emitter junction, but we apply positive to the collector and negative to the emitter, meaning the collector is more positive with respect to the base. Hence, the base collector junction is reverse bias. And so that's why the operation of a transistor is not like two PN junction diodes. It's different. The operating modes depend on biasing. Biasing simply means the DC voltages that we apply or the DC input. And we will discuss this a little bit later in the chapter. So let's look into the operation. And first, let's look into the voltage and current notations. So we still use a 2 subscript notation for the voltages. And if you remember from 201, VXY means we apply positive terminal of the meter to X, meaning the first terminal. the negative terminal of the meter is connected to the second one. So if we say VCE, we are measuring voltage at the collector with a reference at the emitter. And we say VBE, voltage is measured at the base with respect to the emitter. And VBC means voltage is measured with reference to the collector. So please keep that in mind. And then the current directions are IB, IC, and IE. For a NPN transistor, the emitter current is coming out because it's electrons that are coming out of the emitter and going into the base. So the emitter current is coming out. Collector and base are going in. So NPN transistor, NP transistor, IE, the emitter current is coming out. For a PNP transistor, it is going in. Hence, the symbol shows you an arrow. The arrow in a BJT notes that the terminal is a emitter. If the arrow is pointing out, that means it's an NPN transistor because the emitter current is coming out. In a PNP transistor, the arrow is pointing in. And if IE is coming out, that means that IB and IC are flowing in. And for a PNP, they are flowing out. This is the exact opposite. You only need to keep this in mind. And then you can automatically find the others. Okay. All right. So let's go to the next slide where we do the operation, and then I'll come back to these equations. So here you can see base current coming in, IC coming in, combined to form IE. Okay, combined to form IE. And this is a far better illustration of how it actually works. So we have a NPN transistor. We are forward biasing the base emitter junction. So this is the emitter, base, and collector. Once we forward bias the base emitter junction, behaves like a PN junction diode. So the electrons from the emitter cross over into the base. And the holes from the base cross over into the emitter. However, the holes from the base are outnumbered by the electrons coming from the emitter. Some of the electrons from the emitter will recombine with some of the holes in the base, which gives rise to a very small base current. Very small, typically in the microamps. So the rest of the electrons have now arrived into the room. They have nowhere else to go. They have nothing else to do. They are still free to move around. And so at that point, if we now apply a positive voltage to the collector, these electrons are now attracted by the positive voltage, and they cross over the base region into the collector. So even though the collector base junction is reverse bias, because the base is designed to be very thin and very lightly doped, the electrons that have arrived from the base, from the emitter, cross over two junctions and go into the collector, and a heavy collector current results. Electrons go this way, and current IC flows into the terminal. Let's take a pause, think over that. Let me know if you have any questions. That makes sense? Any questions? Nope. Okay. And that's why we can state IB is the controlling current. Small change in IB, excuse me, causes a large change in the collector current. Okay. Large change in the collector current. Then we can go back once more slide and write out this equation. Emitter current IE is the sum of IC and IB. It is true for NPN as well as for PNP. Okay. And then when we apply KVL, we get VCE as equal to VCB plus VBE. Okay. Because the base current is so thin, IB is typically in the microamps. Thus, IC is almost equal to IE. Okay. IC is very close in value to IE, and the ratio of IC to IE is known as alpha, and it's typically 0.99, 0.99 or even higher. The ratio of IC to IB is known as the current gain. Alpha and beta are two of the most important parameters for a BJT. Because IB is typically in the microamps and IC is typically in milliamps, the gain, beta, is typically measured in hundreds. Typically measured in hundreds. So the way this would work with the BJT would work is you would apply a small AC current to the base, and then a amplified output is obtained at the collector. But the way it works, if we were to use this as an amplifier, we would have a small AC signal and would apply a DC biasing voltage, say large DC voltage, and at the output, we'd have an amplified signal. We can say that the transistor would take the DC voltage and give it the shape of the AC input. So AC input would be very small, millivolts or less than a volt. And the DC voltage would be 15, 20, 25, 30 volts or even larger. And the transistor, the BJT, would take the DC voltage or the DC bias and give it the shape of the AC signal. And this, of course, that's a very simplistic way of stating it. So there are 4 operating modes of a BJT. One of those is known as the reverse active. And the reverse active is basically when both junctions are reverse bias. So it's kind of forbidden or basically useless. So we never ever use this mode. Students do study a little bit about reverse active just so they can troubleshoot as an engineer if that happens. So they still need to be aware of. But these are the 3 primary modes: cutoff, saturation, and active. This active is also known as forward active. Okay, forward active. In the forward active mode, the BJT operates as an amplifier, analog amplification. And in the other 2 modes, the transistor is either cut off or in saturation. If it's cut off, we say the transistor is off. If it's in saturation, we say the transistor is on. And then those 2 modes combined, we can operate transistor as a switch, on, off, on, off. And we can use it for digital applications. All right, let's see. Okay. So this is as far as we went in the previous section. So in this section 2, I will stop right here and we'll pick up here again on Wednesday. Again, I'll be in my office starting around 2:30 today. And so from 2:30 to about 3:30 or so. And then next Monday onwards, it'll be Monday and Wednesday morning.